What is the difference and the connections between ANOVA and regression? For ANOVA, we have three treatments such as T1, T2, and T3. They have different means. We use F-test to examine if these means are significantly different from each other. In regression, we have three treatments, and we want to know if the different treatments are related to the mean. So we conduct the F-test to examine the significance of R-squared. These two F-tests are essentially equal. Basically, we want to know if there is a relationship between membership, treatment membership, and the means. Both ANOVA and regression belong to the family of general linear models. That is, we can express the relationship between x and y in a linear relationship. If we remember, the linear model for regression is y equals to a plus bx plus the error. The linear model for ANOVA is yij equals to mu plus tau j plus eij. I means number of individual, j means the group. So ij means which person in which group. If we use our example, if there is a second person in the second group, it would be y22. Mu is the ground mean. Tau j refers to a specific group such as aspirin, Tylenol, or herb group. Tau j means the effect size of that group. E is the error term of a particular person in a particular group. So tau j could range from tau 1, tau 2, tau 3 until whatever number of group you have in your example. So to summarize, the linear model for ANOVA is y equals mu plus tau plus e. We can use a design matrix to indicate the membership used in ANOVA. If a predictor is a categorical variable, in this case, we have three levels: single, married versus divorced. We can create a design matrix to indicate the membership of each participant. The design matrix have first we can create the complete design matrix. It has p plus 1 columns. P equals to number of treatment. Now we have three groups. P is 4. We would have, P is 3, so 3 plus 1 is 4. We would have 4 columns. On the very left side indicates the subject member. In this case, we have 6 subjects. On the top indicates 3 groups. A1 is the single group, A2 is the married group, and A3 is the divorced group. The first column is mu. This is called the ground mean. It is shared by all 6 people. Then the first 2 people under A1, these 2 people are in the single group. So we have 1 under A1, but we have zeros under A2 and A3. Person 3 and person 4 belong to the married group. So we have 1 under A2 and zeros under A1 and A3 for person 3 and person 4. Finally, person 5 and 6 are under A3, belongs to the divorced group. So this design matrix helps us understand who belongs to which treatment. Tau are the effects of each treatment, or the effect of each group. Vector tau of the treatment effect is defined as mu tau 1, tau 2, and tau 3. Mu is the shared ground mean. Tau 1 is the effect size for the first group. Tau 2 is the effect size for the second group. And tau 3 is the effect size for the third group. So y equals to the membership multiply the effect of each treatment plus the error term. For the first person, we will use YY to indicate the first person's score. The first one meaning this is the first person, the second one meaning this is the first person in the first group. Y11 equals to mu plus tau 1, the effect size of the first group, plus E11, the error of this first person in this first group. Moving to the second person, Y21, meaning the second person in the first group, equals to ground mean plus the effect size of the first group, plus the error for this second person in the first group. Then Y12 is the first person in the second group, equals to mu plus tau 2 plus error of this first person in the second group. Y22 is the second person in the second group. Y13 is the first person in the third group. And Y23 is the second person in the third group. Therefore, each individual score could be expressed by such a formula. That is Yij equals to mu, the ground mean, plus tau j, the group effect, plus Eij, the error term related to I person in the J group. Therefore, we can express y using y equals to x multiply tau plus error. This is very similar to the regression equation y equals to bx plus error. We introduced the complete design matrix, the first very squared matrix with all 4 columns. We use this matrix to indicate the membership, so it could be simplified. In the second matrix, we have 3 columns because we get rid of the last column. Even though we don't have the last columns, we still know that the first 2 people belong to the first group, the second 2 people belong to the second group, and the person 5 and person 6 belong to the third group. Therefore, the complete design matrix is reduced to this 3-column matrix. We want to eliminate the redundant information. Then we can further simplify this matrix to 2 columns. We could remove a constant term, that is the ones, because that is the ground mean shared by everybody. It is not unique to anyone, therefore we can get rid of it. This simplified design matrix still tells us the membership completely, and this is called dummy coding. The last matrix also have 2 columns. However, we changed the membership for the person 5 and the person 6 to negative ones. And this is called effect coding. Therefore, instead of giving them a person 5 and the person 6 zeros, we give them negative ones. I will explain why we need effect coding. Dummy coding and effect coding are most popularly used in ANOVA.